S, whatever the command is, put it in buff. Let's say we put it inside of buff. That's the location we put the information. The easiest way to do this is to have a second buff. So what you do is you have the buff, and what you do is you do a string comparison. So inside of here you do a string compare, or a string find, depends on how you want to look at it. You do a string find instead of a string compare. I don't know if string find is built into C. I'm going to assume that it is. String find will find one string inside of another string. That's essentially the basics of it. I don't remember if the string find is first, second, I don't remember the order, but let's suppose that it is. What we're going to do is we're going to look for a 4. If a 4 exists inside of buff, if this is true, what do we want to do? So who doesn't know what the homework is, or the extra credit is anyways? That we didn't even look. Okay, so the extra credit assignment is the command line interface. If you try to write a for loop or an if statement on multiple lines, the interface that is given to you in the book doesn't accept it because it tries to execute a single line at a time. And because it's trying to execute an entire single line at a time, if you write something along the lines of this, for I equals 1, 100, do, let's suppose that's the line you write, it says, oh, I can't finish that for loop because it doesn't have an end, and you don't have any conditions inside of it. So the goal is to be able to write this on one line, the part inside of it in another, for example, print I, and then an end on the third one. And as soon as you write the end, then the entire command is sent. So the easiest way to do that is once you find the for, as an example, then what you're going to do is you're going to copy, string copy, is that what it is? Or copy string? String copy, I think is what it is. String copy, you're going to copy the buff into multi-line storage. So I would define multi-line at the top somewhere like this. It would be char multi-line. Probably something like 2,090 something characters. Some number of characters. 2048. Let's do 2048. 2048 characters. So multi-line would be a large chunk of characters for me to write into. What I do is I copy the buff into the multi-line. I would actually also use some sort of multi-line index, because the multi-line index would say where inside of that multi-line buff am I actually copying. So I'm going to copy every line that they type, I'm going to copy into this multi-line, and I'm not going to execute it. Once I find the end for this for, then I copy that end into the multi-line, and I do the multi-line buff instead of the regular buff. That's the way that I would accomplish the for loop. That's the simplest way. That isn't the way you want to do it in general, because if you have multiple for loops embedded inside of each other, that doesn't work. If you have an if statement instead of a for loop, that doesn't work. If you have an if statement with a for loop inside of that, that doesn't work. So there's a number of ways that this doesn't work in general. But the big idea is you just collect all of your buffers into a larger buffer, and then you execute that larger buffer all at one time. That's the easiest way to do this. If you have questions about how to do that or how to implement that, come talk to me in office hours and we'll show you how to do that. Any other questions about the homework? Awesome. Okay.
I got one.
Yeah.
Is it too late to turn extra credit?
Yes. Okay, so on Tuesday we were talking about objects and object-oriented programming in LUA, right? And we had gotten to the point where we understood that we could create a table which contains all of the functions and all of the variables inside of that object. So for example, we had monkey.
Who's going to provide that?
Monkey.
Oh, yeah, that's fine.
Equals.
I asked that question. The headers,
bananas.
the mass, blah, 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 mass account, and all
Equals
that.
3
That's fine.
with the function throw,
Yeah.
right?
I asked them. Just I forgot to write you about it. I forgot to text you about it.
Does anyone have any questions about this? Everybody's okay with what we did for this part here? We remember all the reason why this is the shortcut for monkey.throw, and we know how to do all that assignment there. Okay, what are we missing from object-oriented programming so far?
Inheritance?
We're missing inheritance. Not only let's do one step even more fundamental than just inheritance. How many monkeys can I have, or not can I have, do I have right now?
One.
I have one, right? With object-oriented programming, aren't I supposed to have multiple monkeys? Much less having to be able to inherit from a parent's monkey of some kind, right? So I need to be able to have multiple monkeys. So let's figure out how to make multiple monkeys. Does anyone have a guess on how I can make multiple monkeys?
Make a table of monkeys.
I can make a table of monkeys. So you're saying like I could have what's a group of monkeys called? It's not a murder. What's that called? Does anyone know? I know. Pain in the ass? Alright. Scary as fuck. How about that? Scary. So we'll have a scary array which is going to be full of monkeys. Here's a monkey. Here's a monkey. Here's a monkey. A troop? Awesome. So we'll have a troop of monkeys. We'll have a troop of monkeys. That created a troop of 3 monkeys, right? A barrel of monkeys too? That sounds kind of like fucked up. I know that barrel of monkeys is a game, but would you really stuff a bunch of monkeys in a barrel? Maybe they're biting you. But... Alright, so how many monkeys do I have? 1. How many times do I use the monkey variable? 3 times. So when we're looking at this, we want to be able to draw the box diagram that I've been drawing before. So if I draw a box for monkey, they have a banana inside of it, which is equal to 3. They also have that throw function, which is equal to this function over here. Right? When I declare this troop table, what I get is I get a troop table, like so. And what are the keys for those three values inside of that troop table? So over here, when I defined my table, I said the key for this value of 3 is bananas. Did I define any keys for these monkeys over here? I didn't. So what are the default keys for monkeys? 1, 2, and 3. This isn't key number 1, this is key number 2, this is key number 3, because tables are also like arrays, but they just start at 1 as opposed to 0, right? And so this is going to be key number 1 is going to be a pointer, not to the function, sorry, to the table monkey. Key number 2 is going to be a pointer to monkey. Table 3 is going to be a key or a pointer to monkey. So how many pointers do I have?
3.
3. How many monkeys do I have?
1.
1. So if I say troop of 2 dot bananas equals 4, and then I print troop of 1's bananas, what gets printed?
4.
The value of 4. Because troop of 2 and troop of 1 both refer to the same monkey. Now we're used to this in object-oriented programming. If you're not used to this in object-oriented programming yet, I guarantee it. There's been a program that you have written that has failed, and you don't know why it wasn't working, and this is the reason why it wasn't working. And if you haven't written one of those yet, you will write one of these programs where object-oriented. You're like, why the fuck isn't this working? Everything's changing when I'm just changing one of them. This is the reason why it's not working. It's because you have an array of something that points all at the same object. Everybody does this, so don't feel bad about it. That's not what I want to do. That doesn't create a troop of 3 monkeys. I want to be able to create a troop of 3 monkeys. If I want a troop of 3 monkeys, besides in code, what do I need to do with my picture? I need pointers to something else. How many boxes do I need total? 3 boxes? So I have 3 boxes on the board right now. Good.
5.
Okay. If 5?
5.
So you're saying write a function that creates a monkey? Yeah, so we're going to get to that in a minute here. We don't actually want to do it that way. We're going to do it a different way, because that doesn't result in the behavior that we're looking for. So we want to have, let's say, five tables. So we want another table over here. Let's put a table over here, and we'll put a table over here. So that's 5 tables, correct? Right?
Mm-hmm.
We want one to point there. Let's make 2 point here, and 3 to point over there. This guy down here wants its own banana, right? Correct? And let's give him a value of 4, because that's what we set up there. And this one will have a banana of 1. And this is also going to have a throw. And this is going to have a throw. Do we want them all to point at the same throw function?
Yeah.
Yeah, sure, that makes sense. I don't want to duplicate that throw function any more than necessary. That works for me. Okay. This is what we want. Now the question is, how do we get it? Now one of the suggestions was we make a function that creates monkeys. We could do that. So we write a function, the function makes a new table. Actually, maybe we should do that. Maybe we should make a function called create monkey that'll do this, so you guys will see what that is. Let's write a function that'll create a monkey. Okay. Function. Create monkey. How do I create a monkey? So the create monkey function is the constructor. How do we actually create a monkey in Lua? What do we need to have a monkey, a real monkey? Not a real monkey, but a monkey box. What do I need?
Banana.
I need a table. And then we need to be able to put the banana in the table, right? So we're going to start with the table. So curly braces. That creates the table for myself. What do I want to do with that table that I created? What now? Put a banana. I can put banana inside of it. Let's say banana equals, let's say 7 for now. What do I want to do with that table? So I'll assign it to a variable. Should I assign this to the monkey variable? Why should I not assign that to the monkey variable? Because it's global, and that monkey table is the other monkey table we defined before. We don't want to override our other one, so how do we make this one not global? We call it local. So we say local monkey. So we make the local monkey table, and this is now our new local monkey table. Then we can say monkey dot throw, and we can either define the new function on the string that does the stuff with the end, the same way we did it before. Huh? No, so the throw is the function. The throw is the function here. Oh, I don't know. What is it? Bananas? Bananas. Yeah. And I can say monkey.throw equals the function, like so. When I do this, I'm making a new function for each one of them, instead of having a single common function. But I can also say, let's suppose there's a monkey throw function or a generic monkey, generic monkey dot throw, which means that I have to define a generic monkey table that has a generic monkey function in it. And I can say end. And then I can return, I have to return the local monkey. So what I can do to generate this is I would say something like this. I would say troop equals generate monkey. comma, generate monkey, comma, generate monkey, like so. That would generate 3 unique monkeys. The way we've drawn on the board with that code over there. I call it crate monkey? Oh, I didn't call it crate monkey. There, got it. Alright, so that allows me to create a single monkey. Or multiple monkeys. Does this allow me to create lizards? No. So if I want to be able to create lizards, what do I have to do if I'm doing this method? I have to make a function called create lizard. And if I want a function that creates macaws, I have to write a function that creates macaws. And if I want a function that... So this ability to create objects is not usable outside of one particular type. So what we're going to figure out how to do now is we're going to figure out how to take a piece of data, which is a table, and then create more objects based upon that table. So this is my original table. How do I create more boxes that are equivalent to that box?
Iterate through the methods or the members of the table and add them to a new generic table?
Yes, is the answer. So that's what we're going to do. So what is that concept called at a high level? Starts with a C. There's 2 C letter words that answer. They're both 4 letters long. Well, one of them is 5 letters, one of them is 4 letters. Sorry. Copy and. What's the other one? Starts with CL. Clone. Copy and clone. We want to be able to clone this monkey. So let's go ahead and write a copy function that's going to copy one table into a new table. And once we write this copy function that copies one table into a new table, essentially what we've done is once we define a table, we can make a copy of it to any other table. And we'll be done. This is our first step. Let's use purple. So let's call this function copy. What is the argument to copy? The table I want to copy. So I'm going to call this T. Copy T. So we're going to copy the table T. We're going to copy it into a new table, correct? So what's the first line of my copy function going to be? The new table. Do I want to say new table equals table? Because this is global still. And I don't know if I use that new table function or variable or somebody else used that new table variable somewhere else. I want to make sure that I keep track of my local variables. And so we're going to declare our variable to be local in this case. So we're going to have the local new table. Now we need to be able to copy everything from table into new table. Does anyone know how to get at the things inside of table, inside of T? So the 1, 2, 3, 4? That's an excellent idea. So what we're going to do is we're going to look at how we would copy it using the indexes first, and then we're going to learn how that is incorrect, and then we're going to fix that copy. Okay? So currently, if we take a look at our monkey, it uses the key bananas, right? That key bananas, is that a number? Is that the number 1? No. So if I ask for monkey of 1, does that give me the 3? No, because monkey of the index 1 is nil. It doesn't exist yet. Monkey of bananas is 3, but we can't get that. So let's figure out first how to copy the elements of a table that aren't keyed on strings. So like if I wanted to copy the table troop, for example, how would I copy the table troop? What I would do is I do something like this. For I equals, what's the first index?
1.
1. 1, comma, because this is a for loop in LUA. When do I want to be finished? Huh? The number of elements in the table, right? Does anyone know how to get the number of elements in a table? No? Nobody's looked that up yet? Okay, cool. We use the number T. That's the number pound sign, number T. This is the number of elements in T. Now, this is not the size of T. This is the number of elements that I can access using our generic numbers 1 through whatever the value is. So for example, if I was going to copy this troop table here, pound sign T would return 3, because 1, 2, and 3 are all valid indices. If I use this pound T on top of our monkey table, how many valid indices are there? 0. So pound T returns 0 on this case over here. That's the reason why this pound T isn't going to work on this monkey over here. How do I now get the things from, assuming that this still works correctly, how do I get the things from here to there? If I was going to just copy an array, how do I copy an array from one array to another array? So the new table of the index equals the existing table of the index. Something along those lines. And you probably want to return the table. This is essentially the copy function for an array in any language. If you look at Java and you write a copy function in Java, you're going to copy from the source array into the destination array. In C, it's the same thing. This is a very generic copy. But this doesn't work when certain things are true. When is it that it doesn't work? If you don't have numbered indices, what does that mean? Maybe we want to use a different word other than indice. What's the word? You want to use the word key, not indice. Now, in an array, the key is the indice. But when we have a table, our keys are not necessarily indices. Our keys are sometimes strings, sometimes they're tables, sometimes they're other things. So what we're going to do is we're going to use a function that will return the keys and the indices from a table. K comma V, I believe it's the keyword in. The function pairs in LUA goes into the table and it finds all of the keys, regardless of type, and all the values associated with all of those keys, regardless of type. And then we'll return them. Actually, maybe it's just the equal sign. No, I'm thinking about it. We'll have to test this in a second here. I don't remember if it's the word in or the equal sign. I don't remember. This might be Python, and this one might be Python, and I have them switched in my head which one is which. So, or maybe it's the other way. I don't know. I don't know. Too many languages in my head right now. So with the K and the V in the pairs, either one of those, the pairs will be, if for example the key is bananas, K will become bananas. And V will become whatever the value of that key is. So for example, if bananas is 3, K will be bananas, V will be 3. If we're looking at throw, the K key is throw, the value would be the function itself. That allows us then to say the new table of something equals something. The new table of what equals what? Sorry? The new table of k equals the value. Because we want the new table's keys to be the same as the old table's keys. And p is the old value. And so we're going to be able to copy that over, like so. This will allow us to copy any table into any other table. This is a cool function. This is a generic copy function. All languages have this kind of function built into them somewhere. I believe it's called clone in most languages. This is the clone function in most languages. If you clone an object in Java, for example, it runs this function. If you call the clone function in C#, it runs this function. If you call the clone function in C++, it runs that function. Yes?
You can still do the do.
Oh, probably. Can you tell me if it's the equal sign or the word in? It's the equal sign?
It works in as well according to
Alright, well I'll just use in. Maybe it's both of them. Okay, now there's a problem with this. Does anyone see the problem yet? This works as written and does exactly what we said it was supposed to do, but there's a problem with this in some way. Sorry?
How do we name it?
Ah, so if we want to be able to make multiple monkeys, for example, let me do instead of the troop case here, let's make multiple monkeys. I would do something like this. So let's suppose I have the monkey table like we defined before. If I wanted monkey A, I could say A equals copy monkey. Now A is a new monkey table, right? I could also say B equals copy monkey. So that's how I would name it, like that. There's another problem with this, though. The reason why, or the problem with this is that this function is technically called the shallow copy. This is the shallow copy function. What does shallow copy mean? And what would be the opposite of shallow copy?
It's not copying elements that can be part of tables.
Your answer may be correct, but you didn't say it very well. Anybody else want here? Anybody else want to give it a shot before you try again? Okay, so try one more time, and then I'll say it the way.
Generally, you'll copy the first level of items if there's tables, and we'll go deeper into those tables.
So if you have a table inside of a table, it only copies the first layer of tables, and that's the problem. So you're correct about that. So for example, let's make some tables up. Let's suppose we have table A. Table A equals the following table. Where inside of A we have inside table. Inside equals this table, which has, let's put some keys in it. Let's put monkey and banana inside of inside. Monkey equals 1, comma, banana equals 2, curly brace, comma, foo equals 3. So our A table. Go ahead and take a second and draw that A table, if you know how to draw that A table with the boxes. Let's see what it looks like. And then I'm going to draw it in a second, and then we'll draw it together, and we'll figure out why this shallow copy only copies one layer, and why this is a problem. So if I draw my A table here, I have in the A table, I have this inside variable, which points at this table here, which has a monkey inside of it, which has the value of 1, and the banana inside of it, which has the value of 2. I also have foo, which has the value of 3. Correct? Does that look good? In the A table, we have this inside thing, which is a table, which has monkey and banana inside of it. If I then say B equals shallow copy of A, I create this new B table, which is my shallow copy. And when I do it, I get every key inside of the original table, inside of A, and I copy it into B, which is whatever the value is. So for example, B's inside becomes pointing at that thing, and foo's inside is 3. A and B both share the same inside table. So if I modify A's inside table, what happens to B's inside table? It's modified as well. And this is a problem. This is a problem because we don't always want to do this. We don't want to allow this to occur. We don't want to allow A and B to have the same piece of data, because so if A and B both carry the same piece of data, that's technically a static member variable instead of a regular member variable. But we don't want that. The way we solve this to go from a shallow copy into a deep copy is we add an if statement inside of this for loop here. We're going to do something like this. We're going to say if type of K is equal to table, then I'm going to get rid of this bottom part so I move it, right? If the type of K is a table, I want to do something special. Else, I'm going to say new table. This is what we had originally. And the rest of that stuff was the same function. So we have this new case in the middle here. What do we want to do in the middle there if the type of K is a table? One second.
You basically do the same thing with the key and values. Create, and then you do a shallow copy of the table, where you basically copy the table into a new table and then take that table and put it.
Okay, so what if inside of this table we have another table called inside is a new table with some other stuff? So I really don't want to just copy the outer table. I want to do what with it? I want to recursively deep copy everything. So you see, that's the answer. There you go. So what I'm going to say is I'm going to say new state, or no table, sorry, not new state. New table of K equals deep copy of D. That'll recursively copy the tables. So that's the deep copy function, and this is the function that almost gets us to object-oriented programming. This allows us to have multiple objects of the same type. This allows us to do almost everything except for inheritance and polymorphism. But there is also a limitation to this, and so this is also wrong. Does anyone see why this is also wrong, besides the fact of inheritance and polymorphism for object-oriented programming? second. Why is this also incorrect? Now, it's not that it's incorrect. This does exactly what we wanted it to do. It made deep copies of all of our tables. And that's what we said. We said, hey, really, an object, or to have object-oriented programming, we have multiple tables with the same members for everything that all point to all the different parts, correct? That's exactly what we said about object-oriented programming is. The problem is that's not actually what object-oriented programming is. When we think about certain parts of that, that is the way that we conceptualize it, but it's not the way that we actually want to implement it. Let's consider that we have the monkey declared, as we declared it before, right? So now I say A equals deep copy monkey, and I have B equals deep copy of monkey. The language that we want to use to describe this relationship is that A is a monkey, correct? We get polymorphism at this stage for free. We don't get inheritance yet, but we do get polymorphism. If I draw the tables, let's draw the tables really quick for this guy. I get monkey as bananas, 3, throw is this function. I have A, bananas, 3, throw is that function, right? I also have B, bananas, 3, throw is that function. Let's do polymorphism real quick. Function A dot throw string and I don't throw string. So let's suppose that the monkey's throw function is I throw string. So if you said throw shit, it would say I throw shit. A dot throw now becomes a new function. Where A now says I don't throw shit instead of I throw shit. That's polymorphism, right? The child is able to redefine the parent's function. That's polymorphism. But let's suppose that I want to redefine monkey in some fashion. If I'm going to redefine monkey, if I redefine monkey's throw, what happens? So monkey gets a new throw, but B doesn't. Can we now still say that B is a monkey? Because B's throw function is not monkey's throw function. And we can't use the child's, or we can't use the parent's throw, because in this case here, the monkey is the parent, or monkey is the parent of B, the way in our inheritance structure. But this B's throw function is still this thing over here, which was the original one, even though monkey changed its throw function. So this is not object-oriented programming. It's almost it, but we can't quite get there. Because what it's doing is, when we have the copies of these throw functions in there, it makes it so that we don't use whatever the parent's is if the parent changes.
write that down.
So, I'll just say it one more time. This is not object-oriented programming because the children don't use the parent's function, even if the children haven't defined their own function. Yes? So we talk about inheritance, and we talk about polymorphism. The children of a class should use the parent's functions if those functions exist, correct? If the child creates a new function of the same name, the child should use the child's function, not the parent's function. That's what it is. Yes, no, maybe so? Ask me again after classes. I'll work with you again. Other questions about this? Okay. So, this doesn't work for us. We're not going to be able to use the deep copy function, even though the deep copy function does mostly what we want to do. The answer to be able to create children of monkeys, or instances of monkeys, is we use a built-in functionality or this concept called metatables. Use a metatable. Before I define what a metatable is, what does meta mean? That's very close, yes. It's a little bit more than abstract, though. A little bit more specific than abstract. So if we say something is meta-information, what does that mean? It's information, but what does it mean about that information? So for example, if you have a website and you have a meta tag on that website, what does that meta tag about that website tell you? That's really what the definition is. When we talk about meta tags or meta information, meta tags are information about information. So when we talk about metatables are tables about tables. So if we create a metatable for another table, what we're doing is we're creating information about that other table. Let's suppose we have table A. Right? Table A is the real table. It has real stuff inside of it. So we could say, for example, it could have height. Let's put the height, let's say 6. It could have width. For the width, let's put 3. We could have a function that would generate area. It would do 6 times 3 would be the area. If it was a cube, we could have 6 times 3 times whatever the length would be. This would be the information that is actually inside of the table. If we wanted to consider that A is actually a kind of a box, what kind of information would we like to know about boxes? So a square is a certain kind of box. Well, what kind of information do you want to know about rectangles? Let's use rectangles instead of boxes. Well, we have the length and the width, height and width here. So we know that rectangles have 4 sides, right? So all rectangles have 4 sides, right? There's no rectangles with 6 sides. But okay, cubes, yes. That's why I switched from cubes to boxes to rectangles. Two dimensionals. Just flat things. Let's do just flat things. So I want to be able to have a rectangle. And I know that rectangles have sides, which is 4. And all rectangles are going to have 4 sides. What I do is I say that A's metatable is rectangle. The metatable for A is rectangle, or rect in this case. What other kinds of meta information would I want to know about rectangles, potentially? Area. So I can have the area, which would be a function that would calculate the area. What do you mean? So A, what we want to be able to say is A is a rectangle. The table rect is a table about rectangles. It is not a rectangle itself.
So rectangle is the meta table. Why does it have things like area which are defined at a lower level?
And so this is a function, right? So when we talk about rectangles, do all rectangles have area? Right? And so that's the meta information. One of the other things is we're actually going to put height and width inside a rect as well here in a second, but that's because all rectangles have a height and all rectangles have a width as well. But the way meta tables work, and this is the way object-oriented programming works as well, is that if the object does not contain the information in it, what do we explore? So not just the superclass, we explore the information that we know about that rectangle. I'm trying to stay away from the word classes and stuff. So if the object doesn't contain the information, we look into information about that object. And so we go and we look at the information about that object. Because that's what a metatable is. It's a table with information about the table. So we have a table, we need some information about that table, we go look at the metatable. Well, we can also make metatables about metatables. So if we don't know something about a rectangle, we can learn something about shapes. If we don't know anything about shapes, we can learn something about graphs. If we don't know anything about graphs, we can learn something about all the way down. This is how we create object-oriented programming. Because if I have multiple tables, I have A table and I have B table, and they both share the same metatable, when I look for information about B and I don't find it inside of B, I look inside a rect. That's the way we're going to do this. Okay. To implement this, we are going to create in LUA, because LUA does not have the concept of objects yet. We are going to create the concept of an object. Does anyone know how to create a concept of an object? An object is a what in Lua? A table. Object is the table. What's the function that we define in, or not define, but the function we use in Java and C++ and other languages typically to allocate new objects? New, right? So I'm going to create the new function for objects. extend this later. We're gonna write some more code. We're gonna start with just this. OBJ in this case is the parent object. OBJ is the parent object. In this function. How do I create a new object or a new table? Make that new table. Same way we did before when we were creating the monkeys and doing the deep copy. Okay. What we do now is we set the meta table of O to object. I believe it is this direction. O, comma, object. Let me look this up just a second. Make sure this is the right direction. I'm not leaving this right. Then we're going to do the following: obj dot underscore underscore index equals obj. This is a requirement of the language. We're not going to discuss what the index function does. If you're interested in what the index function is, you can look in the orange book and it'll describe it in graphic detail. In general, though, the index function is how you do multiple inheritance. It's how you do selective inheritance. It's also how you do public, private, and protected. It's how you do all of those other mechanics. We're not going to cover any of those because that's more difficult than we need to get into. We don't have enough time. We can spend 16 weeks just on this concept of index. Let me look this up real quick. Let's set meta table. So I don't have the wrong order. Okay, we can fix that later. So this is the correct order. O object, that's the correct order. All right, so the reason why this is the order is because obj, let's do ob instead of ob, just o. So ob, it's a little bit easier to see. Ob. Obj is the parent of ob. That's what this set meta table means. Ob is our new table. Ob is what we're going to be doing. This index call allows the parent object to be a meta table. It's a little bit more involved than that, but that's essentially what it is. And then we return the new ob, not obj. We return the new ob, new object. Okay.
Professor,
Yes.
and that's gonna be obj in both of them in the index?
Yeah, obj of indexes itself. This line I don't expect you to understand yet. I don't fully understand what that line does. So it's necessary for now, though. Now the question is, how do I call that? How do I create a new object? So let's suppose I want a new object A and I want to make a new one. Yes?
Can you briefly summarize what that line is effectively?
This index line?
Yeah.
This index line is effectively saying if, when you do the meta table, so meta tables by default, if I'm not able to find it in myself, look inside of my parent. So don't find it myself, look inside of my parent. For my parent, how do I look inside of my parent? Inside of myself. Inside of my parent's self. So, because if you don't have the index, it doesn't work. So like, for example, you have obj here. Obj, does it contain anything? What does it contain? It has the function new, right? So the new object has the function new. Then if I say A equals object dot new object, like so, because that's the way I have to call this. A is going to be this new table here with the meta table of obj, or the object. Obj is over here is object. When I look from A, and I look at my meta table for A is object. How do I look inside of object? That's what index says. How do I look there? And when I do this line, it says, how do I look inside of object? I look inside of object. If I wrote this as a function to say, let me look at the keys, some of the keys you can't access, I now have private members inside of my objects. That's how we create that object. When you read this line, object A equals object.new of object, does this seem redundant?
Yes.
Right? What is this variable? What is this thing here? What are we doing? What are we passing? Huh? So we're passing the table that will be the meta table. That is true, that's what we're doing. But that's not what we're doing. Kinda, but not really. So the things you're saying are true, but it's not what we're doing. And so what I'm asking is, what is this variable? Why is this variable here? To reference it. To reference which thing? The traits of yourself is absolutely correct. So, if you don't get that, the traits of yourself, this is weird. This is a weird concept. It's actually not a weird concept. You've used this a billion times. You just don't recognize it yet. What am I passing to the new function when I make a new object?
The object itself.
The object itself, right? And inside of your constructor, you have a reference to the object itself. In Java, what's the variable that's the reference to the object itself? This. In Java, you have a this reference, correct? You can say this dot, and you can access yourself. That's what you're doing. OBJ is itself. That's what this OBJ is. And so when I say object.new object, I'm saying, hey, I need to be able to have a reference to myself. That's what this reference is, and that's you get it for free. In Lua, when you write it this way, when you write the function this way, you don't get that reference for free. But Lua does have a way that you can get that reference for free. And the way you do this is you use the colon operator instead of the dot operator. So we're going to define our function with the dot, or the colon instead of the dot. When we define the function with the colon instead of the dot, that means that the first argument is going to be a reference to the object itself. And the reason why I keep on saying itself is because the name of the object itself is no longer, you don't have to put in it, you have to declare this in any of your functions in Java or in C++ or any of those languages? No, you don't. So you get that reference for free. It's itself. In Lua, we use the self reference, not the this reference. So we get self instead of object, or this. If I use the word this instead of self here, suddenly now this is object-oriented programming, right? This is how we program in Java. We say this dot something equals something. This dot something equals something else. Instead we use self dot something. But prior to it, it didn't look like, I mean, it kind of looked like object-oriented programming, but it didn't look like object-oriented programming in Java or C++ or something where you had this reference. All I did was I changed that dot to a colon, though. In Java and every object-oriented programming language that you use that gives you a self or a this reference for free is doing exactly what we just did. In Lua, let me write this again larger. A equals object dot new object, and B equals object colon new. Those are identical function calls. The colon says, oh hey, take this thing over here, make that the first argument. What is that first argument? How many arguments does that function take? 1. Right? What's the first argument to this function?
Self.
Self. That first argument is object. Up here, object dot says don't automatically take that as the first argument. Object dot new object. What's the first argument to this function? Object. So those are identical calls there. When you do in Java, if you do an object dot something, so for example, if you have the Java code, you have a Java object class or something, if you have, when you say system dot out dot print line, that's a lowercase p, right? Dot print with some argument there. How many arguments does the print function take? How many arguments do we see to the print function? Like, so if I say, let's make this hello, so it's explicit. How many arguments do you see in the parentheses? 1. And when we talk about in Java, we say, how many arguments does the print function take? We say it takes 1 argument. But that's because Java hides the second argument. It actually hides the first argument. It's hiding the first argument. What is the first argument to print? System.out. This is the first argument that is referenced as the this inside of the print function. This is the second argument, which actually has a variable name. All object-oriented programming languages work this way. There's a function inside of them called the object dispatcher, which does this magic for you. It automatically dispatches this function, which this object is the first parameter, this parameter, and this thing has the second parameter there. Lua makes you can do it explicitly, you can define it explicitly, or you can use the syntactic sugar to hide all that stuff for you. When we get into Python, Python doesn't give you this syntactic sugar. Python just forces you to actually just declare the first argument. And then later, when you use the object dot, you don't have to pass the first argument because this is syntactic sugar. And it's a little bit awkward if you don't know that part. So we're going to get into Python here in a couple weeks, maybe next, well, it depends on how the, we're going to get into Python. And so Python has an explicit self as opposed to a syntactic sugar self. Java has an implicit self. There's no way to do an explicit self, an explicit this. C++ is the same way. C# is the same way. Objective-C is the same way. They all have implicit arguments is the first function. And so this is the way all object-oriented programming languages work. Any questions about where these things are? There. Real quick, let's do a couple of let's see if this one. Let's use these. And then we'll go. I can say A equals object (new). Then I can say B equals A (new). Like so. Who is A's parent? Object. Who is B's parent? A. Right? Because when we look at the new function, the self for the first line is object. When we look at the second line, the self is A. That's all we're going to do today. And this is complete inheritance, polymorphism, everything except for protection mechanisms and everything. That's it. So you go from no object-oriented programming to complete object-oriented programming with just that much code.
It's not over the